This UCSD TV program is a presentation of University of California Television for educational and non-commercial use only.
Well, welcome to the Understanding Climate Change, and my name is Memorie Yasuda, and I'm here for two reasons. I love talking about climate change, so I'm interested in the subject. I also make educational media at Scripps Institution of Oceanography, and my group is called Earth Guide. We make educational materials with undergraduates here at UCSD. So before we start, I wanted to just give you a rundown of where we're going so that we don't get lost in all the information that's there. Basic science, pretty much, I wanted to cover basics of climate change. In learning these materials, it took me a while to figure out how to, put things in context. And so I'm deriving this partly from my own experience, and hopefully it'll be useful to you. Some of these things I didn't figure out till graduate school, and hopefully you'll help students avoid that. So along the way, we're going to hit some standards because they happen to be conveniently there. And then I'll share some visualizations as we go along and some data sets that you might be able to analyze. Generally, I don't have a lot of time for large demonstrations in my own classroom, so little objects that I can use as a basis for discussion, real short discussions, is what I kind of concentrated on. So my presentation is broken into 6 parts. How does sunlight transmit energy across space? It's starting with electromagnetic radiation because a lot of students don't really distinguish what that is, and I found that it was a hard thing. When I was younger, and until I actually got to graduate school, I really didn't know a lot about it because I was a geologist and not a physicist. I didn't take physics in high school. And so one thing that an instructor told me, or a professor actually at Scripps, just made it all sort of fit together. So I wanted to cover this material. How many of you are very comfortable with electromagnetic radiation in here? Okay, great. So some of you and not some of you. So I'll take a little bit of time, and for some of you it's going to be review. How that radiation interacts with atoms and molecules. I'll move on to that. Why that's important is because that's the basis of the greenhouse effect and why we have that. The energy that we have that causes the greenhouse effect, and actually lots of other things, comes from the sun. And so it's the interaction on a large scale, not just at the molecular level, that interests us. So I'm going to move on to that. And then describe very quickly what is climate versus weather, and then show some objects that relate sunlight, the carbon cycle, and fossil fuels. And then I'm going to end with how we anticipate problems, make solutions, and decisions. And that's an open-ended thing. That's just sort of the cap of the presentation, and I don't have solutions, as some of you asked about. So the first topic is, let me go back for a second. So how does sunlight transmit energy across space? What form is that energy in? It's in the form of electromagnetic radiation. You have different kinds of energy. What other kinds of energy are there besides electromagnetic? There's electricity, there's kinetic energy, so energy can assume different forms. Different kinds of waves can transfer energy. For example, a tsunami wave in the ocean, or sound waves. If a sound wave is loud enough, you can actually damage people's eardrums that way, and it can travel across space. But in the case of sunlight, is there anything in the space between the sun and the earth? No, so that's the great thing about electromagnetic radiation. It's the form of energy that can travel through nothingness without intervening molecules or atoms in there. So in this case, What kind of systems depend on the sun's energy on Earth? How important is it? We see on the picture of the Earth the circulation of water in the atmosphere. Just nearly everything. Now, there are a few things that are not driven by the sun's energy. Plate tectonics, geothermal energy, tides, and everything else, the motion of the air, the motion of the ocean currents, nearly all living things on Earth are fueled by the sun's energy if you back it up all the way. So that means even the electricity that we use in many cases is fueled by the sun's energy. So starting with the sun's energy tells us a lot about systems. And some of this energy is used to heat the surface of the Earth and create the weather that we see. What controls how warm the Earth is? And here I'm actually going for a little misconception clearing. If we look at this picture, now this one happens to be one from the late 60s that was taken on an Apollo mission. It's the first time that most Americans get to see, and actually the world gets to see, the Earth as this thing in space. Now, if we look at the Earth and the Moon and all the other planets, now these planets are not spaced out in real space. However, they're in the right order. So the Moon that we just saw in the Earth, are they at the same distance from the Sun? They're nearly at identical distances. So the thing is, if we look at the actual temperatures of these planets that we've now measured, we see that the temperatures are really different on Earth and the Moon. So I pulled this data from a NASA site and then used that other image as a basis of discussion, because the Earth and the Moon are at the same place, and yet it's an example of different temperatures. So distance isn't the only thing. Now, distance does play into this in that Mars, let me use the green pointer, Mars is further from the Sun and it's colder, the high and low. Earth and the Moon are kind of in between, although the Moon gets much colder and much hotter. So, and Venus is closer to the Sun, so it's warmer. Mercury is closer to the Sun and warmer. Venus is unusually warm, even though it's number 2, not number 1 distance from the Sun. So there's something else important that has huge impact on the overall temperatures. Earth, we have this kind of range, and on the Moon, extreme range of temperatures. So if people go there, they need special protection in the spacesuits. And that's kind of an interesting story in terms of physical science. There's all sorts of interesting activities you can base on the spacesuit, because the spacesuit needs to provide an atmosphere for breathing. It has to protect people from certain kinds of rays from outer space. And in this case, there are 2 San Diego astronauts you can find showing these, their suits. Ellen Ochoa from La Mesa and Rick Sturco from the East County, from Lakeside. So those are ways to, engage students also. Why does it not have a minus? And now let's look at the other difference in here. Now we look at greenhouse gases, or what kind of gases are in the atmosphere. This is the atmospheric breakdown of those planets. Again, I took this from a NASA website, and I'll post this website for you so you can pull your own numbers. So the red ones are the greenhouse gases, carbon dioxide and water. Mercury doesn't have much of an atmosphere, and it's actually hard to go to Mercury because Mercury is very hot. Venus right here, 97% carbon dioxide. But so does Mars have 97-ish%, high greenhouse gas. If we look at Venus, the thickness of that atmosphere is 92,000 millibars compared to the Earth's 1,000. So it's about 90 times more dense in terms of, the packing of the molecules, the atmosphere. It has so much gas and it's close to the sun that the temperature is just overly hot, and it diffuses that energy all around the planet to where it's uniformly warm. And another peculiar thing is because the way that Venus rotates, it doesn't rotate every day. Well, it rotates every day for its day, but its day is nearly a year long. So it's extremely long. Now, if we look at Mars, it's cooler than Earth. It's farther away, but this little bit of carbon dioxide, high by percentage, still keeps it a little warmer than it would have been without it. If we look at the Earth, this 0.04%, now I changed it up to 0.04% instead of the 300ths that some tables have, because we're now at, in the high 300s in parts per million of CO2. So greenhouse gas makes a big difference in the temperatures of planets. The moon is cold and hotter because it doesn't have it, even though it's the same distance. So, case of you can use static images to analyze, and then you can, do those thought experiments and critical thinking experiments with, especially with older students in this case, a little bit older. Now, you might see slightly different numbers in these because depending on the mission, the numbers they might have measured are slightly different because day-night temperatures for all these planetary bodies, it's only recently we know, and we've been able to send certain kinds of equipment there to make these measurements. Venus, the other reason, it hasn't, since it's so hot, there's no ocean too. So once the CO2 is there, it gets hot, the ocean doesn't take it up like it does on Earth. So on Earth, we have much more temperate weather, and we have the day-night cycle on top of that. Besides the distance, besides the content of greenhouse gas, we have the rotation of the Earth that makes a difference to the actual temperature. The Earth cools really rapidly. How do we know energy actually exits the Earth system? Well, as soon as you turn off the light by rotating the planet around to the other side, it gets cold at nighttime. Now, these maps are actually forecasts. They're not real temperatures from the National Weather Service, but you can look at these and then show the day-night contrast. And so this is also another resource you might use for planetary temperature. On your website resources, I've also put in maps of the Venus day and night, so you can see the difference there. Venus has that day-night, Mars has the day-night alteration, just like Earth, much more exaggerated. And Venus, from the one south polar image that the European Space Agency made, you'll see that it's all very uniformly cold. So NASA imagery, weather maps, with a few questions ready to analyze, there's lots that students can tease out of this and compare with their thinking. So right now we were just pretending the world is just all based on the energy that comes into that planet. Now, let's say that you have this energy in the form of radiation. Now I'll just use the word radiation to refer to electromagnetic radiation. It can't just bounce off, because if it reflects, you're not leaving the energy behind on that planetary body to heat it at all, so it's not really involved in the weather cycles. So what is it doing? Now first, what are the kinds of electromagnetic radiation? This is a typical diagram, a NASA kind of diagram, and it's kind of nice. It shows the difference between different kinds of electromagnetic radiation that we know. For example, radio waves, AM, FM, microwave, which are sometimes called radar, infrared, the kind of energy that if it lands on us, we sense as heat, visible light, the colors of the rainbow, UV, which is the type that if you have too much of it land on you, if the ozone in the high atmosphere were not protecting us, it would give us skin cancer. X-ray, which is not a good thing if you get too much, and gamma ray, which can come from nuclear reactions, supernovas, and generally is not a good thing for human health. So a different view that I had made that is not quite done, but I wanted to show you a kind of interactive that my group produces, and when it's ready, I'll post it online. On this other diagram, we have this kind of compressed wave like this, but the actual wave for each of these kinds of spectra is of a particular wavelength. For example, radio waves are long, and as we go towards microwave, they get shorter and shorter, and they get very short at gamma ray. Now, all these are moving at the speed of light. You know, technically, there's small differences in how fast they move when they go through different medium. The light does bend, but they're all speed of light, and that's the other beauty of EM radiation. It travels through space really fast, unlike sound. That, you know, sound is so slow that if you're at a concert and you're sitting in the back, you know, you start seeing the lips move at a different time than that sound. But in this case, you can use optic waves to have a phone call to somebody on the East Coast and not hear that time lag. So you have special, machinery, the telephone, that's going to do that transformation of sound to an optical wave. If we look at this energy bar, for gamma ray, it's high, and as we go down this way, that energy is going to go down. So generally, the kinds of parts of the spectra that have longer wavelength contain less energy, so there's a one-to-one sort of relationship to that, and so they're less dangerous. So radio waves, we're bathed in radio waves all day, and it doesn't damage our cells. If you go to the X-ray and gamma ray range, then the energy content is higher, and they will do damage. In the global change, climate change area, the terms that you've probably seen are long wavelength and short wavelength, and that refers to over here. Visible light is the kind of energy that the sun emits. You know, different planetary bodies, well, not planetary bodies, stars will emit different types of light, you know, depending on what it's doing. The sun happens to radiate a lot of visible light, and then the Earth, on the other hand, emits a lot of infrared. So a lot of times infrared is referred to as long wave radiation. Not that it's hugely long, but it's longer than visible. So that's all that's referring to. So what does the sun emit out of that whole possible spectrum? That spectrum is not, you know, all things don't emit the full spectrum. And the sun is emitting things that are in the wavelength right here, between right there and right there, that have a wavelength that's around 1 micron. And these particular colors that you see are particular wavelength waves. And when they strike your eye and they get focused, and then the signal gets sent to your brain, it registers as a color that you envision in your mind. And so that's what you're actually seeing. So the sun also sends a little bit of UV right here that gives you your tan, and that the ozone protects us from, and then also over here in the infrared region. So if we look at what the Earth emits something different over outside of the visible in parts of the spectrum we can't detect with our eyes in the infrared, which is the longer wavelength. The thing now is that we can make instrumentation spectrometers that see in all the parts of the spectra that we're not, you know, seeing with our own eyes, and then we can convert that to visual imagery so we can see what the patterns look like. So if we compare these, energy has been transformed from the visible to the IR. And in the whole greenhouse story, this part comes into the ground of the Earth. This part can't escape back. And we'll look at a few more images for that. I show this because it's an interesting view of the sun. When you look at the sun, you can't see any detail because it's all too bright, and it's not a good thing to do. This was taken with a spectrometer that would look in the extreme ultraviolet. So we saw that ultraviolet's a small percentage of what the sun sends, and if we filter out and ignore all the kinds of light visible in IR, this is a movie of the sun over a 2-week period. And so you begin to see detail in the sun by selectively looking at that spectra. And on this one, sometimes you can ask kids, well, how fast does the sun rotate? And if you look at the timer click by, it's something you can actually figure out. And the sun's rotation is a lot faster than I ever thought it was when I first saw this. It's shorter than a month, than an Earth month. So it's a large object to rotate that fast. So this image comes from SOHO, the Solar and Heliospheric Observatory. They have all sorts of fun images. And so that will be a resource that I will have put online for you. Once you get instrumentation loaded up on ground-based equipment, observing equipment, or from space, then you can begin to see things that we can't see with our very own eyes. On this bottom picture, this is Seawifs' image of the color of the surface of the Earth. It senses, just in a hugely simplified way, for instance, in the oceans, the difference in blueness of the water. And that blueness in the water tells us how many living things are in that water, because photosynthesizers tend to be that brownish green in the ocean, and on land they tend to be green-green. So if you calibrate this instrument, you can estimate how many living things are in a particular patch of ocean or land. And then using satellite, you can estimate the biomass or primary productivity of those areas. So by cleverly using the kinds of radiation that the Earth sends out, you can find out lots of things about different planets. So in this case, if we look at land, you see that the Sahara has low, primary producers, low chlorophyll. And there's lots more in the high latitude. Now, if we go past that and into the oceans, where it's very hard to have a sense for where is it desert or where do you have a lot of plant growth, and the water seems all blue. If we look in the middle of the Pacific where there's nothing, and it's all the same blue-looking water, well, it's a desert, this dark blue right here and right there. But along the equator, there's something going on, and dead on the equator, there's higher, concentration of the cells of single-celled photosynthesizers there than other places. And this is something that satellite measurement reveals. And these organisms that you're looking at are part of the carbon cycle picture. These are the organisms that some people, to reduce the CO2, think, well, if we fertilize the ocean with things like iron and other nutrients that might be insufficient, then maybe we get these organisms to grow faster and we get them to take carbon dioxide out of the atmosphere for us. Well, there's some issues with that, but these are the kinds of images that get you to thinking about all these things that we can do. Because infrared is a kind of radiation sent out or emitted by things on the basis of their temperature, their hotness. We've seen a lot of images where you have night vision. But besides night vision, you can look from aircraft or outer space and look at cities also. And this image I show because this is Atlanta, and the picture actually is called Hotlanta, because it's showing the urban heat island. It's showing differences in temperature emitted by different objects. And this is a good image for analysis too. I think, why are some buildings black versus some white hot? The cool ones, they tend to be these high rises. You know, I don't know for sure, but my guess would be that those are highly reflective maybe. And you'd have to now investigate and look on a website and see, are those glass buildings? And then these ones right here, you know, are they lighter colored, lower buildings? Or is it some other kind of surface? So in some places now, people are planting in urban areas to get this urban heat island effect down, things like gardens and plants. In Chicago, I think they did this on the top of a building to try to get them to make a nicer temperature and not make those places hot. This radiation, you know, the spectrum. I show this because this is how most of us interact with the radiation on a day-to-day basis. This is only part of a giant chart that shows how the spectrum is divvied up. This is a US spectrum chart. So right here, 87.7 to 107.9, this says FM radio. And we have other things like ham radio, navigational beacons. If we looked at this whole chart, it'd have like garage door openers, cell phone, broadband, all these things. So to understand news about these things, kids would need to know about the electron EM spectra. You know, one big thing in the news recently was the analog to digital changeover. And so that went pretty fast. Well, it's because, you know, when you had analog TV and HD TV and digital, it used a wide area of the spectrum. You needed a certain amount of frequencies in there. And so if you make analog go away, you clear up those frequencies and you can use them for wireless and other things and put them on the market to be used for that. So these are big decisions that were made, you know, over a decade ago to do that. And it involved this issue of spectrum, electromagnetic spectrum. So a couple words that come up, transparency and opacity. Transparent means that radiation, you have a material where the radiation travels through and you see it on the other side, you know, if you were standing there. Like this window. The light comes in, it can actually light up objects in that room if it weren't near sunset. And if it were opaque, that light wouldn't get through. And you wouldn't see it. So there are two processes that can happen, or two responses when electromagnetic radiation hits matter. You can reflect it and bounce it back, or you can absorb it. And I wanted to describe what absorption is because it's probably the less familiar of the responses. Here's our spectrum again. In this case, we're going from, let's see, the longer waves are on the right side and the shorter waves on the left side. So it's backwards of the other diagram. And if we look at the visible part of the spectrum, it's coming in from the sun, and we could see it if we stand on the ground. That's true for radio waves too. Radio wavelengths come into the ground. All these areas that are flat right here, these places, those waves don't come into the surface of the earth because they get absorbed and don't make their way down to the ground. So the kind of wavelengths that get to the ground, then the atmosphere is considered transparent to those waves, radio and visible. And then the parts of the spectra that block are considered opaque. So same terms, except now we're using it to describe the whole atmosphere. So this is why sometimes you see these pictures of these big radio telescopes, and this one is the one in, I think, GoldenEye. Seen the movie, the James Bond movie? Yeah. So there are all these big dishes everywhere. if San Diego is too bright for astronomers to see stars, you know, how is it that you can have these big dishes? It's because it's not looking in the visible, it's looking in the radio frequency. So there are objects in space that emit radio, and you can detect those even from the ground. EM radiation wave, when it meets matter, what it does. The first one is reflection. It comes into the Earth, hits tiny objects, large surfaces, it just bounces off and goes back to space. When that happens, of all the colors that are in visible light, you know, sometimes you can have some of them absorbed and go into the material and others reflect. And so the color you're seeing is the one that's reflecting and not being absorbed. This is for something that's, you know, lit from the outside, not glowing that color on its own. And so that's all a pigment does. It's a particular chemical that happens to respond that way to visible light. So on the Earth, we have the ocean that reflects blue, and we have all these other colors. This is not necessarily true color. We have this little thing right here, this shiny spot, which is due to sun glint. In the case of sun glint, it's not just what it lands on that makes a difference in the color, but the angle at which it comes in. If it comes in at a certain angle on a certain material, sometimes you get total reflection and you don't get absorption. So that also makes a difference. This is an actual reflection map, so it's showing what parts of the Earth are the most reflective. The word albedo is used a lot in global change discussions. So the word albedo describes the reflectivity of land or ocean or a surface. If you have sunlight coming in, what amount of it is going to be reflected versus absorbed? So in this case, let's see, a fraction of reflected light is high at high latitudes. So what month is this? So this might be a quick activity I do with my kids. Because one, you know, a lot of times I need to make sure they need to read that chart correctly. And in this case, indeed, if we compare it with the type of cover for that same time period, then you can see this was covered with snow, and you can see the extent of the snow during the northern hemisphere winter. Okay. So that's reflection. Now, absorption and emission. When energy from the sun lands on Earth, then some of it actually, you know, doesn't get reflected and go back to space right away. It disappears into that material, and what is it doing when it goes into that material? It can be used to cause the atom or molecule to move around, or to elevate its electrons from one shell to another. So translation is a kind of motion where the atom moves places. You know, you're moving from one place to another. There are also other kinds of motion like rotation, stretching, you know, and these are all water molecules, moving those hydrogens out from the oxygen, doing this alternately, moving them closer together. So all these motions, they take a particular amount of energy to trigger them. So each compound and each kind of element or atom is triggered into these motions by, you know, I like to sort of think of the magic key that triggers that motion, and it's unique to that material. So if you have a proton, and this is a hydrogen atom, so you have an electron around a proton, and let's say radiation comes in. This is not the magic radiation because it just blew on past. If you have just the right amount of energy in an incoming wave, then that electron will be elevated and moved away to a place that requires higher energy for you to circulate. And then eventually, you know, the real electron's moving a lot faster and we don't know where it is. but it's going to let it go. And when it lets it go, it's going to lose that energy and it's going to have to drop back down to the lower energy state. For hydrogen, we have this one electron, but for larger atoms, you have, and molecules, many of these different electron jumps that are possible. And so each of these requires a certain amount of energy that's associated with a wave of a certain frequency or wavelength. And so it's sensitive to those things. So for carbon dioxide, if it's in the atmosphere and you have certain kinds of infrared radiation coming into and hitting that atom, then it's going to trigger different kinds of motion and activities, and that's going to temporarily hang on to that energy and absorb it. And then eventually it's going to let it go by emission. So you have absorption along with emission. So the atmosphere is transparent to visible. So visible light, whatever's in our atmosphere, nitrogen, argon, oxygen, it comes in, triggers almost none of this kind of activity. But infrared, once that visible light energy has been absorbed by the Earth and it's on its way out and the Earth sends it back to space as infrared, it's a different story and it gets snagged temporarily. So we have the greenhouse effect. Greenhouse gases are those gases in the atmosphere that absorb infrared on its way out. And so they keep that energy around the surface of the Earth longer than it would have been if that greenhouse gas were not there. The greenhouse is not the most perfect analogy, and I had to kind of look up why that is. And because the visible comes in and then the infrared actually can't get through the glass as opposed to being absorbed by the things in the air. And I have the dog there because this is why the cars get so hot on a hot day and why you shouldn't leave your dog in the car, but its window's open. Consequence of all this, if we have the sunlight come through and you take a prism and get it to split up into all the colors, the sunlight, as it passes through the sun's own atmosphere, if you could sort of call it an atmosphere, the gases around it, and other places, it's going to start losing lines of color or in parts that you don't see of the spectrum because those are the things that get absorbed. And then other times, if you look at gases, at parts of the spectrum that are being emitted by gases as they emit, then you might get a distinctive fingerprint for that material. So these effects tell us a lot about the composition, about materials that the light is passing through, and then the materials that are generating these lines. And it's part of the way that understanding things like how a compact fluorescent bulb, which is supposed to help us use energy more efficiently to combat the overall problem, how it works. In this case, the fluorescent bulb, electrons are generated to move along here, and in that bulb there's mercury in the argon gas, and the electrons hit that mercury and give it the energy to emit ultraviolet radiation. That ultraviolet gets absorbed by this chemical, the phosphor, on the inside of the bulb, and it's the phosphor that generates visible light as the end product. And that visible light, it's not exactly like an incandescent bulb. It makes people a funny color because the wavelengths in there aren't exactly the same. So that's kind of an engineering challenge. How do you make a combination of gases inside that's going to be a more pleasant color? It was one of the major complaints against compact fluorescence. This mercury, for people who are interested in it, then that mercury is a neurotoxin and that these need special handling in terms of disposal, because you don't want to create one new environmental problem in trying to cure another one. Photovoltaic cells. The material that coats this, the idea is you want to capture the sunlight as much as you can and change it into electrical energy. So how do you produce something that's going to absorb as many of the wavelengths as you can? So once you understand the concept of emission and absorption, it allows students to have access to all these kinds of other technologies and to think about it. So what happens to sunlight that falls on Earth? Sunlight's been landing on the Earth for a long time. Then usually I ask my students how long do they think, and then that sort of reinforces the age of the Earth thing. And I sort of load up the question and ask them what will eventually happen to the Earth's surface temperature. So then usually I sort of egg them on and tell them about, well, it's been 4.5 billion years that the sun has been shining. Do they think the light's gone out ever? And no, we go no. And so the sunlight's been landing on here, and then we talk about whether energy can be destroyed, or if it can be lost. And somehow everyone knows that energy is not destroyed. And so then, it leaves them thinking, well, it's eventually going to get really hot on the Earth's surface, until the sun dies and disappears. And then we go into the sunlight coming in. Whatever amount it is that we get, the Earth has not, melted down, which it would much sooner if that energy were also not going back out to space. And so the sun's energy that radiates out in all directions, we talk about how we intercept a certain amount of it, and that energy is made out of these waves that we just talked about, the radiation. And we'd set this 100% business. So it's kind of like we get $1 worth of energy out, we have to get at the same rate, $1 out, or else you have temperature problems. The Earth's temperature would change. And no one thinks that's been happening because, we have fossils and continuous life relatively. And then we're ready for this diagram that's really actually complex. And so this is a copy that I've been working on, and it's not finished, but it breaks things down into steps. If we take that $1 worth of energy that came in, then 30% is going to be lost by reflection. It's not going to stick around on Earth and be involved in raising its temperature or anything. It bounces off clouds that are reflective, it bounces off water and land that are reflective, and it bounces off atoms and molecules that make up air. And then we see a bunch of it over here that has absorbed into the ground or other places. So 51% of that dollar, 51 cents, goes into the ground and heats it up. 16% gets absorbed by water vapor, dust, and carbon dioxide. And some of the visible light coming in was infrared, and so if there's any carbon dioxide in the atmosphere, it's going to absorb that by those processes that we looked at earlier. And then we have the material that makes up clouds. In this case, this is water vapor, the material making up clouds being liquid water. And so on this side, let's see, we have 70% absorbed if we add up 51, 16, and 3. Now, in our first diagram, we showed that, well, all of it has to eventually get back out to space, not just the 30% that was initially reflected, or else the Earth's temperature would heat up. So then, the diagrams also show usually outgoing parts. And there are several ways that energy exits the Earth. This 23% that's going out goes out with evaporated water. So in this case, let me highlight this. On diagrams, it's usually labeled as latent heat because it's going to be heat energy that's hidden and been used to lift that water molecule and get it to break off the water surface and become water vapor in the atmosphere. If you try to move gallon loads of water up into the atmosphere, how heavy would that be? Would that use energy or would that give off energy? And so put in those terms, then my students think, well, it would be really tiresome and require a lot of energy to get that water uphill. Well, the evaporative process is actually moving many gallons every day. And so it requires and uses up energy, but that energy is not lost. So when it turns back into liquid water here at the clouds, you get it back. And when you get it back, then it gets radiated and it can go back out to space. Maybe not purely as directly as this is shown here, but all the energy that was taken into the water, the 3% that came from direct absorption of sunlight, the part that got carried by evaporated water into the atmosphere, 26% is now accounted for. This number right here, 21%, is the long wave radiation. That's the infrared radiation emitted by the Earth's surface depending on its temperature. So if you put your hand on asphalt, and does it feel hot to you? So that's the infrared radiation that the ground absorbed on asphalt that's so hot. And you can't see it, but it's actually going back out to space. And so of that, 6% goes directly out to space, and then 15% goes this way. That infrared radiation, because it interacts with carbon dioxide, gets caught up in the carbon dioxide or water vapor again. And it hangs out there for a while until it releases and re-emits. And it's only after several cycles of wherever it's going to circulate that the radiation finally is pointed in the right direction to go back out to space. Because we have this CO2 in the atmosphere, it retards part of the escaping of this infrared radiation back out to outer space. The more CO2 we have, the more this energy hangs out at the surface of the Earth before it finally escapes. Now, after a while, the income and the outgo are going to be the same. It's going to be $1 in, $1 out every time period, but the amount you have in your account that just sort of sits there is going to be different. And so that's going to make the temperature either warmer or cooler. Dave Keeling, or Charles Keeling, is the person who's most well known for his curve, the Keeling Curve, which measures atmospheric CO2. So this is the Keeling Curve. And he's been measuring, he passed away recently, but at Mauna Loa, where the air is a representative sampling of the atmosphere. If you measure CO2 out a volcano or a tailpipe of a car or something like that, your signal is going to be not representative. But Mauna Loa sits here, and it is snow-capped in this picture. Then you're getting a nice sample in the middle of the Pacific. And if we look in more detail, this is what the Keeling Curve looks like. So is carbon dioxide higher than normal? Well, it altogether depends on what's normal. The value we have today, if we extrapolate this line, is about, we're getting towards 390. I didn't check the lab's actual measurements for this year, what it is, so it'd be nice to add that. And we see these little wiggles in here. And then we see that it's been rising steadily over the last 60 years or so. This is a measurement of carbon dioxide from ice cores. How do we know what's normal? We don't know what's normal unless we can go to records that are older and find out what's the variation of carbon dioxide been before people were around to add carbon dioxide to the atmosphere. If we look at the high values here, we have 300. And so 390 is like over here, way up there. And this is a record that's, this dark blue line, at least 400,000 years old. And these are the changes in the atmospheric carbon dioxide concentration with major glaciations of the Earth as they came and went. Now, how does an ice core work? When snow falls on the ground, then the snowflakes are initially fluffy and they land on the ground. There's a lot of airspace in there. And more fall on top of that. And eventually there's a whole weight of a bunch of snow and it squishes those snowflakes together. And in those spaces where there's air, they eventually get closed off. And so you get air trapped in there. And in places for 400,000 years that the snow has never melted, or the ice, it looks like solid ice now, not snowflakes. If you go in there and bring that core back home and sample the little pockets of air, this is the kind of signal you get. And so it tells us what the atmospheric composition was a long time ago. This is the Seawifs imagery in a little movie. And so you see the productivity of land changing over time. And you see greening up of the northern hemisphere during the spring and summer. And you see it moving across the hemispheres. So, when you inhale, you take in O2, and then you exhale, you expel more CO2. In the same way, the planet, by its seasons, dominated by northern hemisphere land surface that has, things growing on it. In the winter, when things are dead and they start decomposing, you release CO2, and in the summer, when you take it up again and grow new leaves, then you take CO2 out of the atmosphere. And with a little time lag, these are the ups and downs that are sort of the exhalations and inhalations of the Earth that you're looking at as we go up this curve. The part that's not normal, at least for the last 400,000 years, is a steep climb. If you had just the cycles of growth and regrowth of vegetation, you get just up and down in a straight line across. So the highest number we saw associated with the glacial, interglacial changes was in the 300s. So all this is above what's normal for at least that part of the history of the Earth, the last 500,000 years. And I haven't checked out, what that's been extended to in detail right now, but I believe it's more than that. Now, does this mean that the Earth is going to warm? That's a big ticket question. Will it warm and how much? Theoretically, by itself, the gas CO2 snags infrared, so it should make it warm. But there are so many other things going on the planet, multiple systems working at once, that it's hard to figure out what the net result is going to be. And you can find aspects of Earth systems that will work to cool and warm, and if you pick them out of context, you could pick whichever way you wanted it to go. But the important thing is to anticipate what is the actual temperature going to be so we can plan accordingly and live to tell about it. Now, what is the problem with fossil fuels? The problem with fossil fuels is multiple. One, we need them because we don't have an alternative existing energy source. And the thing is that they emit carbon dioxide when they're burned. For the same reason that we saw just that photosynthesis and decomposition. Fossil fuels are the leftover parts of living things. And so when you burn them, you're combining with oxygen and enabling the decomposition to get the energy out, just like your metabolism does. The thing is, why is fossil fuel a problem and non-fossil fuel is not such a problem? Well, if you burn wood, like a tree or a log, yeah, it's going to create some pollutants, but the tree grows nearly as fast as you can grow that, if you can burn that wood to make that energy. The thing with fossil fuels, it's a cache of organic material that didn't totally decompose. the leftover squishy parts of dead things that lived in the ocean that still contain the sun's energy within the organic molecules of that body. And so in a flash, in like 150 years, or since the beginning of industrial times, you've taken out a vat load of that energy that was trapped and are burning it rapidly. And so natural systems can't sink that and make that go back away out of the atmosphere into places like new plant growth, because it's way too fast. You know, eventually it's going to go somewhere and things will change and it'll balance out again and drop. But making it go away in the short run is very difficult. And then the other important factor, which is that per capita or per person, you know, where does the energy get used? Millions of kilojoules, well, the highest usage is over here. And low usage is over there. So for people in the world to actually have decent standards of living, it's going to require energy usage in lots of places around the world to bring people's lives, you know, up to a good level. And so at international meetings and organizations like the UN, then people start, you know, how do we solve the CO2 problem? Try to lower the amount of CO2 we emit by maybe things like capping carbon, but then how do we apportion that so everyone can agree? And that was the last part of my talk, that I kind of, you know, solutions and priorities that, you know, I don't have a solution, but that's something for all of, you know, all of us and all of your students that they'll face. And so the carbon cycle diagram, once I post it online for you, I'll try to put a few more details in there. In the media, there's lots of things that you see. You know, one is that, well, if you warm the earth, something might happen, or this might happen, or plants might grow better, so you won't end up with so much CO2. Well, as an individual process that might occur, that's true, but there's other processes that are going to work to enhance warming. For example, if you warm the world, then sea surface temperature goes up. That sea surface is not going to want to hold as much carbon dioxide dissolved into it. And so it's going to also let it go and then create this thing, a positive feedback, that's going to enhance the original effect you were trying to get rid of. And there are other things that are going to go in the opposite direction. And you can't really pick the ones you sort of prefer for your outcome, because the outcome will be what you want it, what it will be. And so I'll close now. Thank you very much.
Thank you.